Hello, my name is Dr. Andrew Rollinson and I'm an energy engineer, and I am researching and project managing the restoration of the Castleford Queen's Mill water wheel. This is a short presentation in May 2015 that describes the work that we've done so far, the research and what our plans are for restoring the wheel. So I'm going to talk about the importance of the water wheel to Castleford and the significance of it in terms of the science and engineering of water wheels. So this talk is also going to talk about a little bit about Old Castleford and a little bit about engineering. Right, the wheel, the Queen's Mill, stands on the River Aire in Castleford, and there's a weir in Castleford, and the weir is not a natural feature, it's been built for the mill. So you can see from the picture that the cross marks the spot where the wheel is. And so what the weir does, the weir lifts up the water and it creates a back pressure to allow the water to flow through the channel and through the wheel housing. As you can see, I've marked it on there called head race and tail race. That channel often goes by different names, but you can see where the water's going there. On the picture you can see the sluice gates, which are not marked. Now what the sluice gates do, the sluice gates allow a fast flow throw of water, and that allows the weir to be repaired, because the weir is just made of stones and wood. So they allow the weir to be fixed. The dashed line marks out the extent of the Queen's Mill building that's now owned by Castleford Heritage Trust. Right, so we're going to go back in time a bit now, and this is a picture of Old Castleford from 1905. And you can see on there that the mill building is still in place, much as it is now, and the weir's there and also the sluice gates. You can see the site of the Roman road and the ford that is about 100 metres to the left of to the west of where the mill is. Interesting features on here is showing the tramway that used to run along Aire Street, and also the ironworks that used to be across the road from where the mill building is. This is going back even further now, and this is from 1851. This is a very interesting map because it shows, as you can see if you look where the river is, you can see the mill building still in place, still as it is now, and you can see the weir as well. So we've got milling going on at this point about 160 years ago. It's interesting for a number of reasons. Is this when you can see that where Castleford train station is now, that's not there. What you've got there, the nearest thing you can see is a brick field, and so this is before the railway station was built, and it's before Glasshouten Colliery was built in the late 1860s. And there's no Beancroft Road either, but what you've got is Beancroft Field. If you look to the right of that picture, you can see Castleford railway station is actually on the junction between Ferrybridge Road and Pontefract Road, so near to where the malt kilns is. What's also interesting on this picture is if you look over where Castleford Bridge is, you can see something marked on there for Castleford Prison, and the Ship Inn, which is obviously now closed, that was there in 1851. Further down towards Weldon Lane you can see the original Glass Blowers Inn as well. Right, this is the earliest map that we've got of Castleford, and this show is from 1817, and you can see at this point Castleford is basically just a collection of little villages where pottery was an industry. So it's before it became a boom town in the Industrial Revolution. But if you look at the river, you can see that there's a little wheel there, which indicates that the wheel was operating in 1817. Okay, back to the present now. The Queen's Mill. It was bought by the Castleford Heritage Trust in 2013, and the aim is to establish a community building for education and to celebrate the heritage and culture of Castleford and for community regeneration. So it's to celebrate all these industries that used to be part of Castleford which have now gone, and to engage the community with all this. The name Queen, I used to know this as Allinson's Mill because Thomas Allinson used to manage this mill for most of the 20th century, but it's called the Queen's Mill because in the late 1800s it was a lot of redevelopment occurred, and they named it after Queen Victoria's Diamond Jubilee. Milling stopped in 2011, but before that time it was actually the world's largest water-powered stone grinding flour mill. Right, moving on to the wheel now. This is the wheel that's in place. It was stopped from turning in the 1970s, and the milling continued, but they used grid electric power. So since the 1970s, that wheel has been just preserved like that, with a little bit of water flowing through it. And so Castleford Heritage Trust are going to restore it, and they're going to use it to generate electricity. But they're going to restore it using heritage techniques. So it's an iron and timber wheel, and they're going to restore it just as it was in the 1800s, to be made of iron and timber. It's a high efficiency wheel, which was one of the reasons it was kept working until the 1970s. And some of the features I'm going to describe to you in later slides, but you can see it's 20 foot in diameter and 13 foot 1 inch across, and it weigh estimated about 25 tons. Right, so before I describe the wheel, here's a little bit of a discussion about why the wheel is there and what it used to be used for. And it's for milling, obviously. And so what milling does, it basically replicates what the molars in your mouth do. They grind up food so you can digest it. And corn is the old-fashioned name for wheat, barley and cereal crops, hence why it was called a corn mill. And so that cereal, you can't chew it, so it has to be ground up, and when you grind it up you can make it into flour, which you can make into bread. And before water wheels, they had a thing called quernstones, which is basically a handheld version, so a person could just turn those around and grind up the corn to make flour. And so obviously it's a low volume process, and having water power allow you to upscale things and generate flour on a larger scale. And this is what happened in the Queen's Mill. So here's a picture of the inside of the mill today, and you can see those wooden structures there. They cover the millstones, and there were 20 pairs of these millstones driven by the water wheel. That blueprint there from 1921, that's when Thomas Allinson had the mill, and it gives you some idea of how it was all connected. The axle of the wheel used to connect with a drive shaft and a very complex, intricate collection of gears that turned the horizontal rotation into a vertical rotation for each of these millstones. The bottom millstone stays in place, and the top millstone turns round, powered by the water wheel. An interesting thing about Dr. Thomas Allinson was that he was a proponent of eating healthy food as an alternative to taking medication. For that, he was struck off the medical register. So it was before people realised that he was actually right. Okay, this is an early picture that we've got of the Queen's Mill, and it's from 1821. And you can see there that there are actually two water wheels. So I don't know how that was configured. One is a corn mill, and one is what's called a flint and bone mill. Now, corn, as I mentioned, that basically just means cereal crops, wheat and barley. But the flint and bone mill, that's interesting. And what they used that for was for the pottery industry, for bone china. Chinese porcelain was being imported around this time and in the 1700s, and the British wanted to make their own, and they discovered that if you mixed clay with bone and flint, you could get a close approximation to fine china, and so they called it bone china. And so that relates to the pottery industry that was going on in Castleford around this time. The earliest records that we have for the mill come from 1698. I should say that a lot of this historical work has been done by a lady called Avril Gibson, who was commissioned to do a historical building record by the Canal and River Trust in 2011. So the earliest records that we've got, and all the documents that remain in the Canal and River Trust office in Leeds, is from 1698, when the mill appeared in some legislation that came before Parliament. Around this time, it's before the steam power, and water power was the main source of industrial power, and so the waterways in the north and the Midlands of England were saturated with water wheels, and there was often complaints about people taking the water rights away off for navigation, and this is one of the cases that came before the Parliament in 1698. The oldest parts of the mill actually still on site are from 1776, which you can see when you stand and look upstream from the water wheel. This is from 1866. This is when some of the major redevelopment occurred. The tenants at this time was someone called Heptinstall. Milling was actually a very lucrative trade to be in, because there was the legislation that if you grew corn or flour or corn or wheat, you had to take it to the local mill, and so the millers became very rich, and so the mill buildings were very well built buildings, and so these are still in place now from 1866. You can see them if you come on our mill tours. Then another major redevelopment occurred in 1888 when somebody called Harry Goodall had the mill, and this is the main 5-storey section that looks out down towards Castleford Bridge and has got Castleford Stone Ground Flour written on it, and that's from 1888, and we still have all the plans for this redevelopment. Okay, moving on to water wheels now, and the science of water wheels. So there were horizontally rotating water wheels from ancient times, from the Roman times, and Scandinavians had them. But the vertical water wheel, the wheel that stands upright in the water, the simplest type of this is called an impulse wheel. And you can see that the paddles or the blades are straight. And so how this worked is that the water used to just flow into the wheel and impact with it. And so the velocity of the water caused it to turn round. These were relatively cheap to build, and they could turn very fast. So the important thing about the equation at the bottom is the velocity of the water. If you increase that, the wheel will spin faster, and so they needed less gearing, but they weren't as efficient as some other types. Now there's a different type of wheel. Right, I should say as well that when the water flows at the bottom of the wheel, that's called an undershot wheel. When it flows across the top of the wheel, that's called an overshot wheel. And overshot wheels work under gravity, so it's the similar type of equation. Force is mass times acceleration, but in this design, it's the actual mass of the water that's important. So it's the mass of the water that falls onto the buckets or the paddles and makes the wheel turn round. These, it was found, were more efficient than the impulse wheels, but they were quite challenging to build because you needed to channel the water above the wheel, and so you often find these up in the dales or where there's a lot of fast flowing water on a steep incline. Right, John Smeaton was what's called the world's first civil engineer. He's a very famous person. He was born 6 miles from Castleford, just outside Garforth, and he did a lot of work on trying to find out what type of wheel was the most efficient, because, as I've said, at this time in this period, it was at the beginning of the Industrial Revolution, and people were trying to get more and more efficiency out of their power generating equipment. And he determined that these impulse wheels were not as efficient as gravity wheels. And another couple of people I want to mention is someone called Carnot and Border, because water wheels were not just specific to the UK, they were all over Europe. They were doing they did some experiments shortly after Smeaton, and they came up with this conclusion, which is important, that the water must enter without any impact and leave without velocity for the wheels to be as efficient as they can be. Now, this is a picture of a different type of wheel. It's a gravity wheel, but the water enters midline with the axis of rotation, so the axle of the wheel. Now, John Smeaton didn't invent this type of wheel, but he was singularly responsible for introducing it and replacing all the undershot impulse wheels with this type of wheel throughout Britain and into Europe as well. And this is the type of wheel that is still in place at the Castleford Queen's Mill. Now, we don't know whether John Smeaton designed it and built it, but it's his type of wheel. And so you can see what's happening is the water is turning much like an undershot wheel, but it's not being turned by the power, the flow velocity of the water. There's a sluice gate in front of the wheel, and that is like a trapdoor that that you can lift up and you can allow a certain amount of water in. So there's always a reservoir of water to come in there. And so the higher you lift this up, the more water can come in. And the water enters into curved buckets. So it's the mass of water that goes in those buckets and causes it to turn round. The curvature of the buckets stop any impact of the water as it goes in, hence the Carnot and Border equation. So it's entering without impact because it just slides inward. This is called a breast wheel because of the stone that closely curves along the circumference of the wheel from the point that it enters until the point that it leaves. Now this is actually part of the civil engineering aspect of where the wheel's put in place, but you can see that there's a closely fitting stone, and what that does is that stops the water from falling out, and so that's the breast in the breast shot wheel. Another important thing about this is it's stood outside of the water, so when the water gets to the bottom it just falls out without any velocity. It just drops vertically downwards and enters the tail race that takes the water away. Now if that wheel was standing in water, the standing water would stop it turning as fast because there would be a resistance to the wheel turning. Okay, now here is the Queen's Mill water wheel, and you can probably see from this the curvature of the buckets. What I also want you to look at is the outer edges. That's called shrouding, and that keeps the water in as well. So without those shrouds, a water wheel is said to have paddles, but with those shrouds it's said to have buckets. You can probably see from this how close fitting it is inside the wheel housing. There's about a 2 centimetre gap on either side. Now this is an efficiency feature, so the wider you can make this, the more mass of water you can get in, and so the more power you can get to turn the water wheel. So that's why it's very, very wide. And you can also probably see from here that the wheel has spokes just like a bicycle wheel, but the spokes are actually on the inside of the shrouds. If you look about mid-centre to the picture, you can see the spoke retainers are on the inside, so that allows you to have a greater width of wheel, so more water coming in, and so more mass, and so more power. You can see these spoke retainers better on this picture, and you can see the curvature of the buckets as well. The timbers on the wheel at present is what's called pitch pine, and this is a high moisture resistant pine wood from America. The spokes are actually made of oak, the reason why I'll come to in the next slide. And it's got these iron spoke retainers in just to keep it all in place and to stop the timbers buckling. Right, this is a plan view showing the water wheel. This was from 1884, so we don't know exactly when the wheel was built, but this plan from 1884 shows it in its present design. So either the wheel was built around this time, or the wheel has basically just been changed periodically throughout the 1800s, so its original design has been lost, but this is showing it in its correct dimensions, 13 foot 1 inch by 20 foot. And so what I'm showing you this for is you can see from this how the gearing worked. So there's a large drive gear which is 10 foot across on the inside of the building, and now we've recently done some excavation, and that's still in place, and we believe the other 2 drive wheels are also in place. This is rack and pinion gearing. This controlled the sluice gate, so it controlled how the water was allowed to enter the wheel. You can see from the diagram from 1900 that there was a shaft that went through the mill building and that turned another wheel, and there was a belt attached to that wheel, and the millers who were working above used to know how fast the wheel was turning because the belt joined onto a bell, and so the bell used to ring periodically as the belt went round, and so if it rang too fast they'd come round and they'd alter the speed of water alter the amount of water that's going into the wheel. So you can see from the photograph that all that's gone now, so that will need a full replacement. And since we're going to use the wheel to generate electric, it's probably going to have some smart control between the generator gearbox and the sluice control, so that it maintains the right amount of flow of water inward. Right, this is looking into the wheel now. This is, I've done all. I've measured everything up because I need to cost for parts for the replacement of the iron pieces and the timbers. So these are what's called the hubs of the wheel, and you can see here as well how the spokes enter these hubs. Now the spokes are made of oak because the weak point in a water wheel is where the spoke joins onto the hub. That's where the main stresses are. So these needed to be of a timber that's tough, and so they used oak. Oak is actually cheaper than pitch pine. So this is showing you the size of things. The two hubs that are on the outer section, so furthest away from the mill building wall, they're single cast pieces, but the two on the inside are cast in half and they're joined together. So I believe that the wheel was actually built in situ with a shaft and the two outer pieces, and then the inner pieces were added and it was built around it. What you can see from here is in the top right hand picture you can see the shrouds and the depth of the shrouds, and you can see a joint. Now there are 8 of these joints, so it was built in 8 segments of these shrouds. What you can also notice are the gaps between what's called the sole plate. The sole plate is the line of timbers that run around the circumference of the wheel, and there's a gap in these sole plates, and that's a ventilation plate. You can see this sole plate and ventilation better on this slide. Now what that ventilation was for, it was an efficiency feature. So this is getting really to the maximum efficiency that you could get from this type of wheel. So it was found that when the water was entering the wheel, if there was trapped air in the bucket, it wouldn't enter as much. And similarly, when the water got down to the base, if there wasn't a ventilation place, suction would stop the water coming out freely. So again, it's going back to this equation. It's got to enter without impact and leave without velocity. Right, this picture here again is just showing the segmentation of the wheel and how it was built. Right, and that's as much as I'm going to talk about the wheel at present, but here's what we're going to do to restore the wheel. We've got some money from something called the Royal Commission for the Exhibition of 1851 to pay for stop logs to be placed in front of the wheel so we can isolate it from flow, so we can repair it. And there's already notches built into the walls, which you can see from these pictures, and they are there for that purpose, to put stop logs in there to stop the water flow. Now because the sluice gate is broken, we need to fix the sluice gate. We could have previously used the sluice gate to stop the water, but we need to do it further upstream, and that's what these are for. And so we've been assisted by the Canal and River Trust with this. We've got one of their chief engineers who's going to help us put the stop logs in place. Before this can be done, silt needs to be dredged from the head race channel, and the Canal and River Trust are doing that for us as well, and then we can start work on it. We're building a teaching community space, because this wheel and the whole Castleford Heritage Trust is about the community, and so we're going to build a teaching space so that people can come and see the wheel being restored, and volunteers are going to restore the wheel in assistance with local building college, so to help build it back to heritage standards. So there's lots of volunteer jobs. We've got to clean out the mill race and clean out the wheel housing and make it nice. Then we're going to begin timber replacement. We've got the sluice gate to rebuild, as I mentioned, and this thing called a cofferdam, which is shown in the picture here. And that used to be a wooden walkway that used to go across the front of the head race, and boats used to moor against this. But it had another purpose, in that there were metal rods that used to go down into the water to stop driftwood and things drifting into the wheel. So we need to put something back across there that's going to stop things drifting into the wheel. And that is it, other than to say throughout this restoration process we're going to be giving lots of tours and presentations to describe our progress and to get the community involved with what we're doing. Thank you.